Hey everybody, welcome back to Basically Science. Thanks very much for being here. Did you know that we took a picture of a black hole? Just think about that. How crazy is that? In this episode, we're going to talk about electromagnetic waves. We have a degree in integrative sciences, which is specifically designed to provide an interdisciplinary education of both physical and life science. We use this education to try and help you understand where the science meets the world around us. If you stick around to the end of this episode, you will understand how we can use a fundamental property of our universe as a method of studying it. Adam, this might come as a surprise to you, but we can see planets that are light years away.
I know. It's
X-rays, we can use X-rays as a tool for medical imaging. You can
right.
have a phone call with somebody that is an absurd amount of distance away from you. You and I are literally talking right now.
Yeah. Through essentially
The ether. No.
electromagnetic waves.
Yes, electromagnetic waves are that sort of fundamental property of our universe
Right.
is a reason why so many things are sort of at our disposal as a means of communication or, like I said, as a medical imaging technique.
Energy transfer.
Yeah, absolutely. Absolutely. For our listeners out there, this also might come as a surprise to you, but trust me, it is real. And if you want to get into some philosophical discourse about like the reality of the situation, go ahead and hit us up on Twitter. But yes, all of the things that I've mentioned have something in common, and that is electromagnetic waves. Electromagnetic waves is sort of like a technical term. That is light. It's sort of like a three-part term. You have electro, meaning electric. You have magnetic, nodding towards some sort of magnetic effect or magnets in general. And then wave. We have some wavy things going on here. Light, the light that you see and interact with, all the colors in their full glory, they're all light waves that are composed of an electric and magnetic component, if you will. And just to throw some more technical terms at you, E&M waves are composed of what's called oscillating magnetic and electric fields. So now we're in the land of fields. And there are all different kinds of light. We can analyze different kinds of light using the electromagnetic spectrum. The EMS is a scientific figure that demonstrates the kinds of light that we know, and that I'm certain that we're confident that there is that's what we have essentially. Like we have this figure, it gives us a whole range of the lights that we know about, and I'm pretty sure that we're confident that that's it. The frequency of the light. Oh yes, I forgot to mention this EMS spectrum. EMS spectrum. The E&M spectrum shows us the lights that we have in terms of their frequencies. The frequency of light, or subsequently the wavelength of the light that you're considering, can give you an indication of the light that you're dealing with. One of the first things they teach you in an introductory chemistry course is that the number of protons that are associated with an atom govern the atom that it is. You know, you have 6 protons, carbon, no question about it. We can talk about the varying neutrons in carbon, but 6 protons, carbon. 8 protons, oxygen. Don't even doubt it. That is the fundamental thing of the atom that we're considering, and that's what makes it that atom. You can think of light in the same way. If you have a light wave that is 220 nanometers in length, sort of like the distance between the peaks of the wave, you have ultraviolet light. No question about it. And that's the defining thing there, much like how protons define the atom that you're sort of dealing with. And, you can talk about more high energy light waves that have higher frequencies. further down the line upon UV light, there's also X-rays, which get like pretty intensely small as far as a wavelength goes, and you can sort of get an indication on the sort of energy associated with those waves, governed by E equals h nu, something that we mentioned in last week's podcast, or 2 weeks ago, excuse me. So that equation there is sort of the mathematical formulation of the phenomenon that we're dealing with here.
And could you break down each part of that in case someone here is new and didn't listen to 2 weeks ago?
Sure, yeah.
What is EH nu?
So E equals h nu. It is a formula, and it's the energy of the photon that you're dealing with.
Which is E, right?
Yes,
E
that's
our energy.
That's equal to essentially a proportionality constant. That's Planck's constant. That's 6.626 times 10 to the negative 34 joule seconds. That is just a constant that pops up all the time in the quantum mechanics, any sort of quantum theory. You're bound to see h. It's also, you'll see h bar, which is just that quantity divided by 2 pi.
Right.
Yeah.
And if you're in gen physics, or you're just breaking in AP physics even, right, you're going to be playing around with Planck's constant, and I can guarantee you're not going to care where it comes from. But you'll eventually find interest in it. Like in the beginning, you just know, okay, it's kind of like Avogadro's number in chemistry. Like, who cares? It's just a number that you need to know. You may not necessarily, like, knowing where it comes from doesn't always help you. In the physical world, if you know where Planck's constant comes from, you're a step above 90% of the people learning physics.
Yes, and all of the work that those, for the founding fathers of quantum theory, all of the work that they did to establish where we are today as far as our understanding of the universe goes, that constant is everywhere. You do any sort of derivation, you're bound to have h bar in there, which is the reduced Planck's constant. Yeah, and then, of course, there's the new part, which is like a script V. It is the frequency of the light, essentially. It's decomposed. It's the speed of light in a vacuum divided by the wavelength of the light. Yeah, so, it's E equals h nu, or it's E equals hc divided by lambda. Just to put it in some terminology.
Yeah, I guess, yeah.
Yeah, sure.
Right, and what we're really measuring with that equation is we are taking a value that we can measure, such as wavelength or frequency, right? Those two values of a wave, we can measure those. We have the ability to do that. And what we're doing is we're taking that piece of information, multiplying it to another constant, and we're deriving more information from it, and that information is going to be energy.
Yes.
Right.
Yeah. To be a little bit more, I suppose, more technical about it, the energy of the photon is like inversely proportional to the wavelength.
Gotcha.
That h right there is the proportionality constant.
Gotcha.
Yeah, you deal with, in math, especially in like mathematical physics and whatnot, you deal with proportionality constants, and that's just one of them. But profound nonetheless. I don't want to like dismiss all of that fantastic work that all of those guys and gals did across the
Right. It's not just
century.
another number.
Exactly. Yeah.